Okay, so the syllabus has your exams scheduled for after today's lecture, but really we needed like today and Monday to get through everything. So we'll see how far we get today, but most likely your exam will be on Monday. We'll see how things pan out, and I'll make an announcement about that. So we're doing the cyclic conformational analysis, so that's really cyclohexane for now. We'll look at these relationships, 1, 2, 1, 3, and 1, 4. So for each of those three, you can have cis or trans. And what we're trying to do is take the flat drawing and convert it into a chair and determine if the substituents are going to end up axial or equatorial. And so when you do that, remember you have a chair flip, so that thing's invert. And then ultimately we want to figure out which of those two chairs is the most stable. So we'll get right into it. This should take part of the lecture, and then the last part of the lecture we're going to look at these other models here that deal with stereochemistry. So that's a new type of isomer. So we left off on the 1,2 di substitution, and we're just using methyl groups to prove the point. So we have two scenarios, the cis and the trans. And what we want to do is take that flat drawing and convert it into a chair. So I'm going to draw one of the chairs, and then I'll just put the numbering inside the ring. And then when I flip that, sort of the carbons on the horizon, one's going to go from up to down and down to up. So, and this is what can get kind of weird about the perspective. So this is going to become carbon 1. So when we flip it, see carbon 1 is down, and then we flip it, it's now up. Carbon 2 is up, and then we flip it, so it's down. So really what's changing is sort of your angle of how you view that chair. And so now we want to put the substituents in. So here is, if you consider the red and the blue as methyl groups, if you're looking at it this way, it's flat. So these are both projected towards you. That's what that bolded line means. And so now we want to draw it like in the chair forms. So really what you're doing, like if you have the model, you're just sort of looking at it now from a different perspective. So if in the flat form, they're both projected towards you, they're on the same side, and I'm calling that side up. In the left-hand chair, right here, that's carbon 1. That methyl group has to be up. So when we draw it, it's going to be equatorial. See how the carbon itself is pointed down? So because it's down, its axial group is going to be down, and that has to be a hydrogen. So that's going to be methyl, and then that's going to be H. Now when we go clockwise to carbon 2, the methyl group is on the same side as the C1. So that carbon is up, so the up group is axial. That has to be methyl, which makes them on the same side then. And now the hydrogen's down, it's equatorial. When we do the chair flip, so this would be an example of that So if the blue is the axial methyl and the red is the equatorial. So when we chair flip it, the red's going to become axial and the blue's equatorial. And so we have to represent that now in the chair flip on the right-hand side. So this equatorial methyl is now going to point up because that carbon's pointing up. It's axial. And then the axial methyl on C2 now becomes equatorial. So those are the two chair flips. And overall, we would say this is like equatorial, axial, axial, equatorial. Whoop. So in terms of the A values, you always have one that's axial. And remember, an axial substituent experiences that A13 strain, which makes it less stable. So for these, you don't really win in either conformation. So let's do the trans one. So carbon 1, notice how it's still bolded, it's pointed out towards you. So it'll be the same as the case above, it's going to be equatorial. And that hydrogen's axial. But now this carbon 2 methyl group, it's a dashed line, so it's projected away from you. So now it's facing the bottom of the ring. So when we go over to carbon 2, it's got to face the bottom, so it's going to be equatorial. So hydrogen is axial, methyl group is equatorial. So we would say E. And then when we flip it, they both have to change their position. So they have to go from equatorial to axial in both cases. So axial is now up. And then down on C2. So you have axial, axial. In that isomer, comparing the left and the right chairs, the left one would be more stable. Because in the right one, the axial methyl groups are both going to experience 1,3 interactions with the hydrogens. So let me draw those in blue. And so that's a destabilizing factor of those two conformations. So really the message of this, when you draw your chair, you have to look at, is the carbon pointing down or up in whatever chair form you draw? And then remember that a carbon that's pointed up, its axial bond is up. Carbon that's down, its axial bond is down. And so that will help you understand what is conveyed by this bold or this dash meaning. And we'll revisit, this bolded and dashed bonds when we get into stereochemistry as well, when we start thinking about the three-dimensional space of the substituents. So we'll do some more practice on this, and we'll have some questions just to interrogate the chair a little bit more. So it's now a 1-3 relationship. So it says on carbon 1, there's an ethyl group, and then carbon 3 is a methyl group. So we want the cis isomer. So we'll draw the bold to indicate that they're both on the same face. I'm gonna, for this, the chair form, I'm gonna put the numbers sort of different, just so you can see it. It really doesn't matter how you put them in there as long as you get the relative relationships right. So I'll start with 1 over here. Just to show some flexibility in how we think about this. So in the flat form, it's showing that the ethyl group is up. So on this carbon here, is the ethyl group going to be axial or equatorial? What? It's got to be equatorial, because that carbon's down, the axial bond is down, that has to be hydrogen. And then the up bond is equatorial, which corresponds to that being up. So for the C3 methyl group, we want that to be on the same side. So we go 1, 2, 3. We want the methyl group up, so it also has to be equatorial. That makes them on the same face. And then both hydrogens are down or axial. So here we end up with equatorial, equatorial. Then if we ring flip it, those substituents have to both go to axial. So axial, and then axial. So A, and we look at that and we would say the left one is more stable. So in general, you want as many substituents equatorial as you can get. So we can use some logic to say that for the trans one, they're both going to have one substituent axial and one equatorial, because we already know that looking at the cis conformer, we have to flip one of them. So we'll keep the ethyl group the same. That's going to be up. And now when we go over to carbon 3, it's on the different face. So now the hydrogen's up, and then that methyl group is down. So we have equatorial, axial. So we can ring flip. Again, carbon 1 will go up. carbon 4 will go down. So the ethyl group ends up axial, and the C3 methyl group will end up equatorial. So in either of these, you're really not winning in terms of which one's more favorable, because again, you can approximate like an ethyl group is the same as a methyl. So it's really not favoring one side over the other too much. Any questions? Yeah. So again, in these two, if you approximate this ethyl group as just methyl, neither one is going to be, it's not going to be a majority of one over the other. Because again, for this one, even though it's bigger, these two hydrogens are pointing into the ring. And so you don't really win in saying like this would be more stable just because it's equatorial. They're probably about the same. I mean, there's a subtle difference, but it's not going to be like 90% this, 10% that. This one. So here you have, I'll draw it in blue. So on that top face, remember the top face has 3 axial substituents, so does the bottom. On the top face, 2 of them are alkyl groups, methyl and ethyl. Then you have this hydrogen. So the methyl group has that 1,3 interaction. Then it has that with that bigger group. So that's reciprocal. And then the ethyl group also has that. So the 1,3 diaxial interaction is destabilizing. Because imagine if this is a bigger group, they're like parallel to each other, so they want to repel. And so that steric interaction is strained. When they're both equatorial, so you only have hydrogen interactions. Those are smaller and they're not really repelling one another. So again, the models can help you in one sense getting the relative locations, but in terms of the size, it's never really representative of the true size. Yeah. Well, if you had like each carbon has a methyl group, yeah, that would be, you would eventually end up in a conformation that would have like 1, 3, 5 diaxial or triaxial. That would be pretty destabilizing. Once you get beyond 2 substituents, like it gets a little bit more harder to analyze and predict, because then there's the subtle differences in the size, and then when you do the chair flip, you still have to determine, axial, equatorial, and then really of the 2 chair flips, you want to put the most in equatorial. So that's going to be the most favored conformer. So this is just a summary of the 3 substitution patterns. So 1, 2, 1, 3, and 1, 4. And again, I didn't draw it in here, but if you say that's X and Y, whatever they are, you can have them cis, so they're on the same side or face. Trans, that's what we mean by, the bold versus the dash. And then for each cis and trans, you have the two ring flips. So for example, in the cis one here, the 1, 2, no matter what, you end up with a substituent that's axial. In the trans one, you have di-equatorial. So that would be favored over diaxial. So some of them are clear, but most of them are basically the same. So you could memorize this graph, but really the key is noting the relationship, the relative relationship 1, 2, 1, 3, or 1, 4. Are they cis or trans? And then converting it into the chair. So which of the following conformers of the 1,2-dimethyl cyclohexane is the most stable? So on here, there's the two cis and the two trans. So out of all of them, D would be the most stable. Because both substituents are equatorial. So here you have an axial, here you have an axial, and there you have an axial. And so that automatically adds an energy penalty relative to the di-equatorial. So here's sort of a logic test. You're given a flat cyclohexane, and then which one of the responses represents the chair form of that drawing? What? D? No. A. So I'm going to say this is up, that's up. Now when we look at A, if your eyeball is like right here, sort of looking down at the face of the ring, you see that is up and that is up. The reason that D is not correct, that group is down. So this would be equivalent to the trans isomer. What's wrong with choice B? So we're looking at a 1-3. This is a 1-2 relationship. And then C is also incorrect because it's a 1-4 relationship. And so that's the B and C are kind of the derailer answers that you can expect on the final exam. Like, it's just sort of simple accounting of the relationship. So don't get fooled by those. So A and D are really what you're choosing from, and then the logic comes in with, understanding what is meant by those bolded and dashed bonds. So here we have so cis 1-tert-butyl 4-methyl cyclohexane. And it's asking how many axial hydrogens does it have? So we know that for an unsubstituted cyclohexane C6H12, there's 6 axial hydrogens, 6 equatorial. In the molecule that's shown, the C4 group, that's a methyl group, right? So we've basically taken 6 minus 1, and that's going to get us 5 total axial hydrogens. So we have the 2 on the top, and then the 3 remaining on the bottom. So I know this might seem like minutia or very small details, but again, when you start learning reactions, it's important to know the disposition, whether it's axial or equatorial of the hydrogens, and then which hydrogen is going to get acted upon. So we kind of already answered this, how many are on the top? Again, that group is already axial. So there's 6 total axial. We've replaced 1. And of the 6, there's 3 on top, 3 on bottom. And the 1 that we replaced was on the top, so that gives us 2. So there's 2 axial hydrogens on the top face. So the same molecule, but now we want to determine the relationship between HB and HD. So if you imagine you're looking down that carbon-carbon sigma bond in terms of a Newman projection. What's the angular relationship between HB and HD, or stated in another word as one of the responses? Anti? So I'll make the blue group. I have it. So that's up, down. So the blue group's going to be the tert-butyl group. And then the red group's going to be the methyl group. So red is methyl, blue is tert-butyl. And we're interested in HB and HD. So you're looking at it one way, but when you look at it rotated, the Newman projection this way, so you're looking down this carbon-carbon bond, this hydrogen to that one, going from here, rotating the angle, that's 180 degrees. So those are anti to one another. So we have HC to HE. And if we were looking again down that bond, what is their relationship? So essentially C and E are both equatorial, so di-equatorial. What's their angular relationship? So they can't be eclipsed, right? Because you have one that's up and one that's down. We already saw for the prior problem, the trans diaxial, that was anti. They may or may not be best friends, so the answer is gauche. That's 60 degrees. Because you have one that's up, one that's down. If you're looking down this bond in the Newman projection, the angle is this. So that's 60 degrees, that was gauche. So this is HA to HC. We have an axial and an equatorial. Both are down. So down and down. We know it's not, the angle can't be 0 because that means they're eclipsed. And in terms of this H carbon, carbon H, it's got to be a multiple of 60 degrees. So it can't be 109. We know they're not anti because they're on the same face. They're both down. So that's also 60 degrees or gauche. So now you're looking at this hydrogen and this one. So that angle of rotation is 60. So that's gauche as well. And so this might be the tricky one. So D to E, what is that angle?
180.
It's not 180. It's 109. So the trick there is I didn't say dihedral, I just said angle. So that's your normal bond angle. So HE to carbon to HD. That's bond angle. So for, again, a dihedral angle is like HE, carbon, carbon, HB. So bond angle has 3 atoms. Dihedral angle has 4 atoms. I think this is the last of that, yeah. So just real quick, as we saw originally in the cholesterol steroid nucleus, you can have multiple rings attached to one another. So a common sort of fragment or substructure of organic molecules is when you have 2 6-membered rings bonded together. So we learned about these bicyclic compounds a little bit in terms of the nomenclature. You have a 6-membered ring, a 6-membered ring, and that center carbon-carbon bond is the bridge. So this molecule by itself is called decalin. So you can have cis-decalin where the 2 hydrogens are on the same side, or trans-hydrogen, they're on different sides. When you convert that system into chairs, it turns out only the cis-decalin can undergo the ring flip. The trans-decalin cannot, due to that ring juncture. It will not allow one of those rings to flip to the other chair conformer. So we would say this is locked. And this is conformationally mobile. And again, if you go on to like take medicinal chemistry or toxicology, pharmacology, the reason that's important is sometimes you want to have very rigid structures for small molecule drugs. So there's not a lot of conformational mobility, because a drug basically interacts with an enzyme target that has a certain spatial volume to it. If you want the drug to fit in there, you don't really want it flopping around too much, because then it might not fit too well. And if you've taken like biology, you might have heard of this like lock and key mechanism for drugs and enzymes. Like the key fits into that lock a certain way, and you don't want too much variability in the functional group shapes. So next slide. Questions before we totally switch gears here?
Could you just go through with like how to tell the difference between equatorial and axial? Because at first I thought it was like the axial is like just pointing straight down or straight up. Is that the difference?
That's pretty much it. So in your chair, so maybe what I'll do I'll say is a key, I'll label blue carbons as up. So there's 3 of them. Those carbons are up. So the up bond there has to be axial. And then these green ones, green is down. So that the axial bonds have to point straight down. And then when you go back to fill in your equatorial ones for each, it's got to be the opposite. So, for example, this blue bond right here, that's axial, it's up. So the equatorial has to be down. For this green one, the axial bond is down, so equatorial has to be up. And then as you go around the ring, they alternate. So down, up, down, up, down, up. Is that a Lil Jon song? All I do is win, up, down. So my advice is just practice. Draw your chairs and then draw the substituents in. And really going from the flat to the chair is whatever the substituents are. You just hydroxyl group, amino group, ester, whatever. The important thing is to realize you have this top face, the bottom face, in sort of these different right and left sides. Okay, so with that, we're now going to progress into another form of isomers called stereoisomers. And to learn this, we're going to use halogens as our sort of element that is going to indicate to us there's a complication with the stuff that we've learned so far. So to incorporate a halogen into a ring as a substituent, you're really dropping the I and E and then adding O. So fluorine becomes fluoro, chlorine becomes chloro, bromine is bromo, and iodine is iodo. So now we're going to use those as substituents in the nomenclature. And we'll consider these 2 monohalogenated alkanes. And we can go through the the degrees of unsaturation argument. All we've done is swap an H for a halogen, and we find there's no degrees of unsaturation, so we don't have to worry about that. And so the question is, how many constitutional isomers can you draw and name? How would you differentiate them by carbon and proton? How do you determine if the halogen is present in the molecular formula? And again, that was, we used mass spec to determine that.
What does that say, the mono?
Monohalogenated.
Okay, thank you.
So I point that out specifically because really this compound right here is the one where we're going to see where the issue is. The C4H9Cl. And then once we learn about the monohalogenated variant, we're going to do a dihalogenated variant of that to see how complex things can really get. So for C3H7Br, how many constitutional isomers exist? This is our normal sort of exercise. So we know that for 3 carbons, it's a propane derivative. Then we see where can we stick the bromine. So we can put it at carbon 1, or we can put it at carbon 2. So that's 1 bromopropane, or 2 bromopropane. You can't draw anything else without violating a Lewis dot structure. So that one's fairly straightforward. So what about C4H9Cl? So 4 carbons, that's telling us it's butane. So the names are going to end in butane. So we can put the chlorine at position 1. So that's 1 chlorobutane. Or we can put it at position 2. That's 2 chlorobutane. So I'm calling those linear, where all the carbons are in a line, but then we can have branched. And these would be propane derivatives now. So we have a methyl group and a chlorine to put in. The methyl group has to go at position 2. And then we have the chlorine we can stick back in. We can put it at 1. So that would be 1 chloro, 2 methyl propane. And then the last one is 2 chloro, 2 methyl propane. So we come up with this seemingly correct answer is 4, but I'm telling you now that it's more than that, because there's an issue with one of these. That's the new concept. So far all of that's correct based on everything we've learned. But really it's this compound right here where there's an issue. So the 2-chlorobutane. And this is just a summary slide of what we just did, where you see the total number of carbons. That gives us the parent. So C3 is propane, C4 is butane. The C4 is when we can have linear versus branched. And then you see the naming of getting the halogen substituents in there. So I think the next couple questions, this one. The proton NMR belongs to one of those C4H9 constitutional isomers. So let's just draw the structures in so we can refer back to them. So given the proton NMR, which isomer does that belong to? I don't think so. A would be a good approximation. So how many total signals do you see in the proton? So we'll write that down. 4 unique signals. And then let's just go through the responses, determine the uniqueness sets. So 1-chlorobutane has 1, 2, 3, 4 sets. 2-chlorobutane, 1, 2, 3, 4 sets. 1-chloro-2-methylpropane, 1, 2, 3. The methyl groups are the same. So this one's out. And then 2-chloro-2-methylpropane has how many unique sets? What? 1? So again, don't get confused about, like, it's a static drawing and that can confuse you. But if you're standing on that carbon and you look out, you see chlorine, methyl, methyl, methyl. It doesn't matter which methyl you're looking at. They all end up being the same. What can be confusing, like if you start here and you say, well, I walk over to there, this makes that different, that makes that different. So you're really looking for symmetry. So this has 1, so that's out. So the 4 and the 4, now we have to do a little bit more digging of what differentiates them. So the answer is not A, because you see this signal right there? Those H's belong to the carbon that's bonded to the chlorine, because that carbon's different, right? That's why it's so far away from the other ones. If you look at those, there's 2 hydrogens. How many neighbors does it have? Just right here. So yeah, for this one. So there's 2, so 2 plus 1. That should be a triplet. But when you look at the actual data, you're seeing, I'll take my glasses off here, 1, 2, 3, 4, 5, 6. So then you sort of reverse the n minus or n plus 1 rule, right? So that proton is the one we're interested in. It has 3, 4, 5 neighbors, so 5 plus 1 is 6, so that better matches this. So sometimes you can get away with just counting the number of signals, but if you end up with the same thing, then you have to dive a little bit deeper. So that's the one we're interested in learning more about. We'll deal with, or I guess it's and let me just draw something on here to show you why that is. So that carbon 2, we know it has 2 hydrogens. So if we draw those hydrogens with one coming out towards you and one going away, this representation of that bond does not really match that, right? This just straight line. We interpret that line to mean in the plane. But in reality, there's two hydrogens. So that means that chlorine can be substituted there or there. And you end up with two things. And technically, they're not the same thing. But they have the name 2-chlorobutane. So you can't have two different things with the same name. So there has to be some other way of describing what's happening. So we kind of already did this exercise just with that proton. We said of the isomers, this had 4 unique hydrogen sets. This one also had 4. This one was 3, and then that one was 1. So let me redraw that 1, 2, 3, 4. So at carbon 2, we're going to substitute each H for a chlorine. So overall, the molecule is 2-chlorobutane, but we've drawn 2 things. In one of them, you have the chlorine projected out towards you. The other one, with the dash, it's going away from you. So these are called stereoisomers. All of the connectivity is the same. Carbon 2 is still bonded to chlorine. But what makes it different now is the spatial arrangement of where that chlorine is. Sort of a little bit more nomenclature. We would call that carbon atom 2 a stereogenic carbon. And what does that mean? That overall it has 4 different substituents. So if we're standing on the carbon and we look out, we have chlorine. I'm going to use the whole thing, ethyl, methyl H. So that's 4 different substituents. Now when we stand here, we look out, the chlorine's pointed a different way. Chlorine, methyl, H, and ethyl. So with this model kit, I have these directions that always confuse me. So the white is just the yellow for purposes of what's on here. So the white is in my left hand, the blue is in my right. Make sure one of those carbon, and make sure one of the carbon bonds is pointed up. So I'm going to point that one up. So what color atom is projected away from you? So the red. And then, am I doing that right? I always get confused on this. So if I'm doing it that way, let's just think of that as hydrogen, because that's going to be important when we learn the rules. But you have 1, 2, 3, 4. Now if I keep if I overlap the yellows and the blues, so I don't have two left hands, but I'm holding like those two the same. Notice the relationship between these. The spatial arrangement's different. So I can overlap the yellow and the blue, but I can't get overlap between the red and green. So stated another way, this bond to rotate. Those are mirror images of one another. So just like your right and left hands, like are mirror images, you can't overlap them like completely. Like you can't. That's not overlap because I have my palms facing different ways. So those are mirror images. My hands, just the subset of my body. Like in theory, your body itself has an internal mirror plane if you slice it that way. Like on the external part, your organs are not mirrored, right? You have two lungs, you only have one heart. So internally, your organs are kind of asymmetric. But you have the four substituents in their mirror images of one another, which means you can always overlap two of them, and then the other two are going to be spatially different. So in terms of a one carbon atom with four substituents, just to keep things easy, we're going to have a hydrogen, and then we're going to use three halogens, fluorine, chlorine, and bromine. So the H and the F, they're drawn the same. So they're in the plane. On this one, the bromine is projected towards you. On this one, the dashed means it's away from you. So the relationship between these, again, it's the same connectivity, but the spatial orientation is different. So they're called stereoisomers. There's four substituents, H, F, Cl, and Br. So that's a stereogenic center. And the question now is, how do you differentiate them? How do we even know they exist? So we learned the normal nomenclature rules. Now we can differentiate them using this subset called Kohn-Ingold-Prelog. And I'll just, for the rest of the semester in Organic 2 as well, I'll just call it the SIP rules. So really what we're identifying is the carbon atom. And so we said there's four different substituents, and then we assign a priority to those substituents based on, and this is the important part, the atomic number. And that's the number you see next to those atoms. So hydrogen is atomic number 1, fluorine is 9, chlorine is 17, and bromine is 35. So that, again, that's the atomic number, and then from that, what we're going to do is assign it a priority. And so priority is based on increasing atomic number. So what I'll do is I'll just write as our key the blue number I'm going to write is the priority number. So because bromine is the highest, that gets priority 1. Then chlorine, then fluorine. Hydrogen's the low man on the totem pole, so it's 4. So 1, 2, 3. And now the key part of this, which is what's different than what's shown on this slide, but you'll see it on the next slide. So I want this one. So this one is what is shown on the left. So as you look at it, the hydrogen's in the plane of the screen. Now to do this rule properly, the model helps. You're taking the lowest priority group and then you're looking at it this way, so through a Newman projection. So the lowest priority group is always facing away from you. And then what you end up looking at is sort of like a steering wheel. So 3 atoms. And then you're seeing which way those numbers in blue rotate. So this is the compound on the left. So priority group 1, that's bromine. 2 is chlorine. 3 is fluorine. So 1, 2, 3. So that means you're going clockwise. And that's defined as the capital letter R. So clockwise is R. And then make sure I'm doing the mirror image of this. So got that right. I want to hold red, green, blue. Okay. So this is R, and because this is the mirror image of it, the direction of those numbers is going to go the opposite way, so counterclockwise, and that's designated as S. So clockwise is capital R, counterclockwise is capital S. By show of hands, how many people are right-handed? How many people are left-handed? You see the difference, right? It's interesting to think about. I mean, it doesn't have to be this way, right? When we say clockwise, it's going like we understand it to be that direction. And so in the evolution of humans, like because more people are right-handed, that's considered like normal. So this is a Latin, the R comes from the Latin rectus, and the S, do you know what the S comes from? Anyone? Any lefties? So the S comes from sinister, that means evil. So it's going the opposite of what's normal. I didn't make that up, that's just the way the R and the S work. So just keep those things in mind. Clockwise is R, counterclockwise is S. The main thing is the lowest priority group has to be away from you. I mean, you can, like with this one, so that's the R. So 1, 2, 3, it's going clockwise. If the lowest priority group is towards you, you're still assigning that priority, and then whatever direction you figure out, you just flip it. Because if you do it now, it's going to be S, so you just flip it to R. But if you have the model, you stick the lowest priority group away from you, you'll always get it right. And so now we have a method of distinguishing these two compounds. And we put that nomenclature R and S. So one of the skills you need to be able to do is if you're given a name that says R something or other, you need to be able to draw it using those wedges and dashes. So I'll make a note. One stereogenic carbon equals 2 stereoisomers. So you have a stereogenic carbon, you end up with 2 stereoisomers. Because they're mirror images, they have a special name. They're called enantiomers. So enantiomers are stereoisomers that have exactly opposite R and S designations. So you might think, well, like whoop-de shit, but now think about when you have a molecule that has 2 stereogenic centers. How many total stereoisomers do you get? You get 4. Because you have 2 centers, you can have R and R. Its enantiomer will be S and S. Or you can have RS, its enantiomer will be SR. So you can have 2 stereocenters, 3. I mean, there's molecules with like 20 stereocenters. So you can get a lot of different relationships. So you need to be able to look at the name to tell if they're enantiomers. We'll talk about what the other relationship is if they're not enantiomers. Look at the name, look at the structures based on the wedges and dashes. Are they mirror images or not? So that the other issue here is you have these 2 molecules, and what I've done in the table here is just listed some properties. So this is for the R enantiomer, this is for the S. And basically what you see on each entry, so molecular weight's the same, melting point's the same, boiling point, density, carbon shift, proton shift, everything is the same, but they're 2 different molecules. So how in reality do we know that they actually exist? So there's only one instrumental technique that will determine that, and that's called polarimetry. So did you guys do polarimetry? So you did like glucose or something?
We spun the whole thing.
So you were doing something, but you didn't understand the context in which you were doing it. Okay. So notice here, so there's your R, there's your S, but now notice there's something else in the name, this sign right here. So a negative sign, a positive sign. That sign comes from the physical rotation of light. And what I want to be clear about, R and S, that's something you determine from atomic number in priority. Like, that's a human construct. This sign, minus or plus, that comes from a physical measurement. Furthermore, do not assume that R is always minus and S is always plus. It has to be measured. So with a stereogenic center being R, it does not imply that it's always minus. It has to be measured. So the rotational sign, negative or positive, is measured using a polarimeter. And this will be a crash course in what that is. So the light that's coming out of the ceiling here is it's white light. So it has all these other wavelengths in it, right? Like if you put a prism up, it can be separated into different wavelengths. So a polarimeter is using a specific wavelength of light. But light in general has two fields to it, an electric field and a magnetic field. And so what you'll notice in the red field, this is like your normal like sine wave looking curve. Then in blue, that's 90 degrees to that. That's the magnetic field. So in your standard sort of white light scenario, even though you're seeing these just couple select red arrows vectors, really it's a lot. So within that circle, there's just a lot of them. You can put a filter on there that polarizes the light. For example, see this arrow here? The filter is taking out all these other vectors that are occurring. So you're only getting one of those. I don't see anyone. Does anyone have sunglasses? If you want to hold up a pair of sunglasses. So when you wear sunglasses, what are they doing? They're filtering out a lot of the light so that it's not hitting your eyeballs and you have to like squint and your eyes hurt, right? So it's the same principle. It's just filtering out a certain vector of light. Now, I know it's a cheap drawing from your textbook, but if you consider that vector as, say, 0, it's one direction. So you have this one directional light, then you're going to put a sample there of your compound. And after that sample, you're going to analyze that vector. So this is your light source with all those different electromagnetic vectors. This is the polarizing filter. Notice that sort of that up and down vector is the only one that gets through. Then in here is your sample as a solution. That light's going to go through there, and notice that when it does, it's tilting. So now it tilted to a different angle. And then this thing is how you analyze the light coming out of that. So if the light is tilting clockwise, it gets a plus rotation. If it's tilting the other way, it gets a negative rotation. And so these have certain words attached to them. So plus is dextro-rotatory, and then minus is levo-rotatory. So again, that's something that has to be measured. And so we have about a minute left. So I think this was the R enantiomer, this was the S. Say your R enantiomer, you run it in the instrument, it rotates the sample, say it rotates it in the plus direction. The enantiomer, the S, it has to rotate it in the minus direction. So you get a plus, you get a minus, and then you have some number afterwards. That's the magnitude by which that vector moves from its origin. So say this was plus 50, this would have to be minus 50. And so there's the three scenarios: the pure sample plus 50, the pure sample minus 50. And then what we'll pick up on next time is if you have an equal mixture of this and this, plus 50, minus 50 mixed together, overall in the polarimeter, the reading is going to be 0. So there's the three things we'll calibrate ourselves to. Then we'll look at mixtures of these things. And so that's called enantiomeric excess. And then we'll also finish up on, now we're gonna add 2 stereo centers to the molecule and see what other relationships develop from that.